Welcome back students to the video lecture series. I am Adil Mansoori from Civil Engineering Department of IJ Institute of Engineering and Technology. So we are discussing unit operation processes for wastewater treatment. So up till now we have already discussed about two processes, that is screening and the grid chamber. Okay, we have already studied why these processes are required and also the design criteria and numerical related to these units, that is the design of these units, have already been covered. Okay, in this video we will see some more processes related to wastewater treatment plant. So let us begin. Okay, so today we are starting with a new topic, that is called equalization. Flow equalization is damping of flow rate variation so that a constant or nearly constant flow rate is achieved. This technique can be applied in a number of situations depending upon the characteristics of collecting system. You can see the location of equalization basin in the figure. Okay, so dear students, you can see that the first unit is the screen and then there is the grid chamber. Okay, above grid chamber there is a small graph which states flow rate versus time. Okay, so we all know that throughout the day the flow of the wastewater is not constant. In the early morning till 12 o'clock the wastewater generation is high, right, and so the flow will be increased. Then up to certain period the flow of wastewater will reduce and hence it will again increase in the evening. Okay, so the flow of wastewater coming into the wastewater treatment plant is usually fluctuating, right? So the main function of the equalization basin is to maintain the quantity of flow. Okay, so you can see that the location of equalization basin in the figure is after the grid chamber. Okay, so it is clear that wastewater entering the grid chamber has varying discharge with respect to hours of the day. Okay, but after the equalization basin the wastewater discharge is form of subsequent unit. Okay, so you can see that after the equalization basin, when there is a flow measuring device, right, and above the flow measuring device there is again one chart which states flow rate versus time, which is showing it is nearly constant supply, right? So that the main function of equalization is to maintain the constant supply to the subsequent unit, that is the primary sedimentation tank, then trickling filter and secondary sedimentation tank, and so on, right? Understood students? So the main, okay, so this is again another type of equalization basin, right? Next is location of equalization basin, right? So in some cases the equalization basin may be provided after preliminary treatment, that is primary treatment, and before the biological treatment. Equalization after primarily treatment Equalization after primary treatment causes fewer problems with sludge and scum, right? And in case the flow equalization tank is to be located ahead of primary settling tank and biological treatment system, the design must provide for sufficient mixing to prevent solid deposition and concentration variation. Okay, so it is also necessary to provide aeration system to avoid odor nuisance. Clear students? Next is volume required for equalization basin. So the volume required for wastewater flow equalization tank is determined by using an inflow mass diagram in which cumulative flow, that is inflow volume, is plotted versus time of the day. Okay, and the average daily flow rate is also plotted on the same diagram, which is straight line drawn from origin to the end point of the diagram. Okay, so let me show you the diagram. Okay, so here, dear students, you can see that this is the cumulative inflow of wastewater in meter cube. Okay, and on x-axis there is the hours of the day. Clear? Now, when you plot, that is the inflow of wastewater versus time, then you get this curve, right? Okay, and when you join the first point and the last point, then you get a straight line. Okay, and on the curve where there is the maximum curvature, that is this particular point, okay, you need to draw a tangent. Okay, so after drawing the tangent, the distance between the tangent and this line will give you required equalization volume. Okay, similarly in this also, so here when you plot cumulative inflow of wastewater versus time, this is another case where you get a curve which is S curve, right? So here there will be 2 points, right? And at both the points, that is this particular point and this particular point, that is the maximum point, right? So you have to draw tangents as at both these points, and the distance between these tangents is the required equalization volume. Okay, so in order to find the volume of equalization basin, you should know the total inflow of wastewater for the entire day. Okay, clear? So next is data required for design of equalization basin, right? So first one is the hourly flow data, that is wastewater discharge during midnight to 1 o'clock, 1 o'clock to 2 o'clock, so on till the 23rd, that is the 11 p.m. to midnight. Okay, so you need all those datas, that is hourly datas. Okay, then design criteria of competent agency of state, that is Bureau of Indian Standards or GPCB or CPCB, that is Gujarat Pollution Control Board or Central Pollution Control Board. Okay, then you should know the location of the equalization basin in the flow sheet, right? Then list of details like manufacturer of equipments, pumps, pipes, as well as prices of the equipment should be known. Clear, students? So these are the sum of data that is required for design of equalization basin. Okay, students, so our next topic of discussion is the sedimentation tank. Okay, so sedimentation is the physical process and it is unavoidably used in case of wastewater treatment, right? In sedimentation process, the heavier organic and inorganic particles settle down at the bottom of the sedimentation tank, right? To achieve the removal of settleable particles, to achieve the removal of suspended settleable particles of desired size, the wastewater is retained in the sedimentation tank for a fixed time, which is known as detention period, right? So detention period is nothing but the time between entry and exit of the water, okay, or a particle. Clear? So the upper clear water is collected from the tank, and at the bottom of the tank there is formation of sludge because of the settleable particles, right? And the sludge is drawn out from the bottom through the pipe called sludge pipe, right? So let us have a look at the diagrams. Okay, so here you can see that this is the influent, right? Clear? After equalization basin, the next treatment is the sedimentation tank. So this is the influent, right? Influent will enter the sedimentation tank through the central pipe, right? And after detention, clear water, right? Effluent or clear water will be removed, right? And whatever the particles that have settled down at the bottom of the tank will be removed, which is known as the sludge. Okay, so clear? So let us now have a look at the types of settling tank. Okay, so types of settling tanks based on nature of working. So first one is the fill and empty type, then continuous flow type, then based on location in treatment plant, that is preliminary settling tank, which is also known as grid chamber, then primary settling tank, then secondary settling tank. Okay, then based on shape of the tank in plan. Okay, so first one is the rectangular tank and circular tank. Okay, so these are the different types of settling tank based on nature of working, location in treatment plant, and shape of the tank in the plan. Okay, let us move ahead. So first one is the continuous flow type tank. Okay, so in this tank the wastewater is continuously supplied at one point called inlet, and the same after treatment leaves continuously from the other point, which is known as the outlet. Okay, so the wastewater entering the tank is called influent and leaving the tank is known as the effluent. Okay, so let us have a look at the plan of the circular tank. Okay, so here you can see that there is an influent pipe through which the wastewater will enter, right? And from here, right, the clear water will be removed. Okay, and whatever the scum is there, right, it will be removed from here, right? And whatever the sludge is settled down at the bottom will be removed from this pipe. Okay, sludge pipe. Clear, students? I hope it must be clear to you. Okay, so this is the section of the circular tank, right? So below this tank there is an inlet pipe which will lead to the center of the tank, right? And from there water will enter into this circular tank, right? And sludge will get settled at the bottom of the tank, right? And it will be removed from this sludge pipe. Okay, and the clear water will be removed from this effluent channel. Okay, and scum, that is the foam that is produced, will be removed from here. Okay, clear, students? So let us now have a look at the informations required for design of primary sedimentation tank. Okay, So average and peak design flow including return flow from other treatment units like activated sludge plant and trickling filter should be known. Okay, then treatment plant design criteria prepared by competent authority, that is Bureau of Indian Standards or relevant IS codes. Okay, then in case of expansion of existing plant, the information about it should be known, right? Then topographic map of the site should be known and the shape of the tank. Clear? Then data of influent pipe, that is diameter, flow characteristics and approximate water surface elevation or hydraulic gradient line. Okay, so this is one of the important information that is required, because without this you won't be able to design a primary sedimentation tank. Okay, then head loss constraints for sedimentation facility. Okay, so these are the different informations that is must for design of primary sedimentation tank. Clear, students? So let us move ahead and start with the settling velocity of the particle. Okay, so the first one is for the particle size less than or equals to 0.1 mm diameter. Okay, so for that Stokes law is usually governed. Okay, then second one is for the diameter of the particle greater than 1 mm, right? For that Newton's law is governed. And third one is for the diameter of the particle in between 0.1 mm and 1 mm, right? So for that Hazen's equation is governed. Okay, so let us have a look at the equations. So first one is the Stokes law, where settling velocity will be given by Vs equals to G by 18 nu, right, into G minus 1 into d square, right, where G is the gravitational acceleration, nu is the kinematic viscosity in centi-Stokes, capital G is the specific gravity and d is the diameter of the particle. Okay, then second one is the Newton's law, where settling velocity will be equals to under root of 3.33 G d into G minus 1, right, where G is again gravitational acceleration, the diameter and capital G is specific gravity. Okay, and according to Hazen's equation it is 60.6 into G minus 1 into d into 3t plus 70 upon 100. Okay, students, where T is usually 27 degree centigrade. Okay, the rest everything is same. Okay, students, so let us start with a new topic, that is design criteria of sedimentation tank. Okay, so first criteria is the surface overflow rate, right? Here there are two conditions, that is without sludge return and with sludge return. Okay, and there is a given range of surface overflow rate, right, and there is a common value that you should adopt for design of the sedimentation tank. Okay, so let us have a look at it one by one. So the first one is for without sludge return, right, and there are two conditions, that is average flow and peak flow, right? So for average flow the rate or the range of surface overflow rate is in between 30 to 50 meter cube per day per meter square, right, and you can go for common value as 40. Then for peak flow it is in between 70 to 130, right, and the common value you can go for is 100. Fine. Then talking about with sludge return, then for average flow it is in between 25 to 30 meter cube per day per meter square, and common value you can go for is 30. Fine. And next is peak flow, where range is between 45 and 80. Okay, and the common value is 60. Okay, so this is one of the design criteria of sedimentation tank. Let us have a look at other criteria. So second one is the detention time, right? So detention time for water, that is wastewater in sedimentation tank, is in between 2 and 2.5 hours. Okay, and common value you take is 2 hours. Fine. Then velocity is in between 0.15 to 30, right? Clear? There is no common value. The range of velocity should be in between 0.15 and 30 meter per second. Okay. Then dimension of the tank. So for rectangular type, length should be in between 25 to 60 meters. Then L to width ratio, that is length to width ratio, should be in between 1 to 7.5 is to 1, and common value you can go for is 4 is to 1. Okay, then length to depth ratio is usually 4 to 25, and common value you can go for is 7 to 18 is to 1. Okay, then width should be in between 3 to 24 meters, and common you can take as 6 to 10 meters. Okay, and depth should be between 2.5 to 3.5 meters. Okay, and you can take as 3.5 meter. In case the circular tank is to be provided, then diameter is 3 to 60 meters. Okay, and common value you can go for is 10 to 40 meters. Talking about depth, it should be 3 to 6 meter deep, and common value is 4 meter. Understood, students? So this is about the design criteria of sedimentation tank. Let us now have a look at the design steps of sedimentation tank. Okay, so the first step is assume the detention time. Okay, then find out the capacity of the tank, that is the volume of tank. Then assume surface overflow rate, then finding out the surface area, then finding the depth, then assume L is to B ratio, then provide additional 4 meters for inlet and outlet arrangement. Okay, and provide 1 meter for sludge accumulation and 0.5 meter for freeboard. Clear? So let us now move towards the numerical. Okay, so numerical states Okay students, so the numerical says that design a primary sedimentation tank of rectangular shape for a population of 40,000 people and with a water supply of 135 LPCD. Okay, so let us start with the solution. Okay students, so here they have given that water supply of 135 LPCD. Okay, and population is 40,000 people, right? Now, if water is supplied to the 40,000 people, then how much quantity of water should be supplied? So you can write that total water supplied will be equals to 135 into 40,000, right? Now according to the thumb rule, right, according to the thumb rule, 80% of water supplied is generated as wastewater, right? So total wastewater generated equals to 0.8 into 135 into 40,000. Clear, students? So this comes out to be equals to 4320 into 10 to the power 3 liters per day. Okay, so this is nothing but 4320 meter cube per day. Clear, students? Now first assumption, that is assume detention time, right? So how much is the ideal value? It is 2 hours, right? So therefore capacity of tank will be equals to 4320 divided by 24 into 2, right? That means this quantity of wastewater is generated, right? It means this much quantity of wastewater has to be passed through the primary sedimentation tank for the entire day, right? So if I divide it by 24, then I will get capacity of tank for 1 hour, right? But I want it for 2 hours, so I'll multiply it with the 2. Clear? So this comes out to be equals to 360 meter cube. Okay, so this is nothing but the volume of tank. Clear, students? So let us move ahead. Now next step is to assume SOR. Assume SOR. They have not given any condition, so we are assuming 30 meter cube per day per meter square for PST with sludge return. Okay, and we are considering it as average sewage flow and average sewage flow. Okay, so now we know that SOR is equals to Q by A, right? So therefore can we find out area? It will be Q by SOR, right? How much is the discharge? It is 4320 meter cube. Upon SOR we are taking it as 30, so we will get 144 meter square as the area. Understood, students? Now we need to find out the depth. Okay, so we have got volume equals to 360 meter cube, right, and area equals to 144 meter square. So can we find out depth? Therefore depth will be equals to volume upon area, that will be equals to 360 upon 144, and this will be equals to 2.5 meters. Okay, clear? Now we need to find out length and width. So next assumption, assume L is to B equals to 4 is to 1, right? So therefore L by B equals to 4 by 1, that implies L equals to 4 times B, right? Now therefore area equals to L into B, and that is nothing but 144 meter square. In place of L I will put 4B, therefore 4B into B equals to 144, therefore B square, or I'll write directly as B equals to 6 meter, and therefore L will be equals to 4 times 6, that is equals to 24 meter. Clear, students? So here we got L equals to 24 meters, width equals to 6 meters, and depth equals to 2.5 meters. Clear? Now suppose you were given that design a circular tank, right? So I'll just write over here, for circular tank we need diameter, right? So area we already know, that is 144, right? So therefore pi by 4 d square equals to 144, therefore d will be equals to 13.54 meter. Clear? Right? And we need to provide depth accordingly from the design criteria. Clear? Now one more thing that we need to provide is, coming back to the rectangular tank, one more thing that we need to provide is additional length for inlet and outlet, right? Therefore provide 4 meter length for inlet and outlet, right? Then what else do we need to provide? We need to provide depth for sludge accumulation and freeboard, right? So provide 1 meter for sludge accumulation and 0.5 meter for freeboard, right? So therefore what will be the total depth? Total length first. So first total length equals to 24 plus 4, that is equals to 28 meters, and total depth equals to 2.5 plus 1 plus 0.5, that is equals to 4 meter. Okay, so what will be the final dimensions? Final dimensions of primary sedimentation tank will be equals to 28 meters by 6 meters by 4 meters, where 28 is length, 6 meter width, and 4 meter is depth. Clear, students? So this is how primary sedimentation tank is designed. Okay.